Hey everybody, how's it going? I want you to buckle up on this particular lesson because it's, how do I put it? A lot of people have spent a lot of time doing the first worksheet. And I think that the amount of time everybody's spending on the worksheet is a great thing because learning to do all those things shores up a bunch of miscommunication. People at this stage of the game are way better at doing the basics of algebraic basics and algebraic reasoning than any time I've ever taught the course before. But another reason I'm super pumped at how much time everybody's spending on the first worksheet trying to get it all down, get it all mastered, is because those skills come up in practice in today's lesson. And it's, how should I put it? If you mastered all that, then what I'm going to say today will be totally cool. And if you're still going back and forth about mastering it, well, I mean, you made it past the first exam thing, so you can probably do something. Essentially, we're going to use those skills and put them into practice, okay? So at the end of this, you'll be able to, essentially, we can write quadratic functions in one of three different forms. Three different forms that tell us something useful. Something called the standard form, the general form, and the factored form. You've already seen the general and the factored form before. The standard form is something new. So at the end of this, essentially this is going to be a great big thing where I tell you the different skills. You can use factoring to go from general to standard, general to the factored form. You should already know how to do that. Complete the square to go from general to standard. We're going to talk about that. I want you to be able to, and then we're going to do something really cool. We're going to interpret the behavior of the function by just looking at the algebraic expression. This is a whole new, really cool skill that I want you to learn. It pays dividends down the road. So we're going to talk about recognizing the behavior of the function just by looking at the equation. It's super useful. It should take some time. In my mind, that's the aspect of the skill that's going to take the most time. But if you can do it, fantastic. You'll have leveled up. And then we're going to use the essentially deal here is that each of these forms gives us a piece of information about what the polynomial function is doing. So we're going to use the standard form to find the vertex, the maximum and the minimum, factored form to find the roots, and use the general form to find the Y-intercept. Okay? In other words, the way we write our quadratic polynomial will tell us different information. It will make different aspects of this super apparent. Somebody wrote no on the live chat. Well, I'm sorry, Air Popo, but you gotta learn this. Buckle up. So let's start with an example of what we're talking about. Dig this. Y is equal to 4x minus 2, x plus 3. Y is equal to 4x squared plus 4x minus 24. And y is equal to 4 times x plus 0.5 all squared, 25. Okay. What you see here looks like three different functions. We're going to talk about these as functions the same way we talked about, linear expressions as functions. Instead of relying on function notation, I'm saying y is equal to an expression involving x. And we're going to call that our function. So these three look like three different functions. I mean, look, they're super different. But it turns out they're all the same function in different form. Before we go any further, I want to demonstrate to you that they're the same function, and we're going to do it by writing it in this form. Just like in that first video, you expand the polynomial to be able to compare them. So let's expand these. This one becomes 4 times, all right, x times x plus 3 plus minus 2 times x plus 3. 4 x squared plus 3x minus 2x minus 6, which becomes 4 times x squared plus just x minus 6, and then multiply through that 4x squared plus 4x minus 24. Each of these coefficients match, and so it's the same polynomial. Okay. What about this one on the right hand side? That squared is shorthand for x plus 0.5 times x plus 0.5 minus 25. We'll write that out. I'm going to give myself a little bit more space. 4 times x plus 0.5 plus 4 times x. Oh, wait, hold on. I made a mistake. 4 times 0.5, x plus 0.5 minus 25. So this becomes 4 times x squared plus 0.5x, 4 times, well, you know what? I'm going to do it a different way. I'll run out of space like this. This becomes 4x squared plus 4 times 0.5 is 2x plus 2 so this becomes, it's important to take your time when you're expanding, just because, boy oh boy, 2x plus 1 minus 25. So now we can combine them all. 4x squared plus 4x minus 24. As we see, the exponents are all the same as these ones, so it's the same. Okay. So as I said before, what we have here are 3 different versions of the same polynomial. Why would we bother writing 3 different versions of the same polynomial? Won't one do? Well, the answer here is that each of these polynomials, just like with linear functions, how you can write a linear function in general form, or point-slope form, or slope-intercept form, and each of those tell you a different piece of information. In this case, each of these is a specific way of writing our polynomial, and it tells us a different piece of information. What piece of information does it tell us? Well, let's go into their names first off. This is called the factored form, and we've already met the factored form. The factored form makes roots obvious to us. So the general form of a factored form polynomial is a times x minus x0 times x minus x1, where x0 and x1 are the roots. So if I look at this expression, I can tell from this that x is equal to 2 and x is equal to minus 3 are the roots of the polynomial. Okay? The second expression is called the general form. The general form of a polynomial is essentially what we talked about in the very first expression. It's some number times x to the power another number times x to the power 1, another x to the power 0, right? So the general form of this of a quadratic function looks like this: ax squared plus bx plus c. I'm deliberately using capital letters right now, just because there was a little bit of confusion really early on, and I don't want to deal with that. Okay. What does the general form tell us? Well, there are 2 specific numbers that really tell us information right off the bat. There's this number and this number. The value c, we'll get into this a little bit later on, but the value c is our y-intercept. It tells us where the graph of the function is going to cross the y-axis. Alternatively put, it tells us the output of the function when the input is equal to 0. So if you want, you can think of that as the starting value of the function. The letter a, the coefficient in front of the x squared, it tells us about the shape I'll be going into this in more detail a little bit later, but if a is a positive number, it means that the graph is pointing up like that, and if a is a negative number, it means that it's an upside down U. Okay? Last I expect, this is called the standard form. This one is most like the point-slope form of any of the different expressions. The recipe for the points, the standard form is a times x plus, wait, it's minus, right? Yeah, sorry. Got to get these signs right. Minus h plus k. Okay. So in this case, the value of a is equal to 4. The value of h is equal to minus 0.5, and the value of k is equal to minus 25. The standard form tells you what the minimum or max value is. Depending on the context. Furthermore, so in this case, like I said, I'll be explaining this before, the maximum or the minimum value here is 25. It happens when x is equal to minus 0.5, so that's when the function is at its either maximum or minimum, and then the value of a tells you whether it's a maximum or the minimum. So in this case, because a is positive, y is equal to minus 25 is the minimum. Like I said, I'll be explaining where all this comes from in a few moments. But the overview here is that the function can be expressed in 3 different ways, and each of these different ways make a specific part of how the function behaves and what it does apparent to you just by looking at it. The same way looking at the point-slope form of a linear function tells you exactly how that thing's going to behave. In this case, all 3 of these, depending on the form of the polynomial, how it's been arranged, tells you different and important information about the behavior of the function. Okay? So that's the overview. We're going to go into it. General form is ax squared plus bx plus c. Standard form is ax minus h squared plus k, and factor form is ax minus x0, x minus x1. Okay. So there are 3 different forms that our polynomial can take. Before we go on, I want you to remember a lesson we talked about in the factored form. Not every quadratic can be turned into the factored form, right? Have factored form. So some of them do and some of them don't. Whether or not they do or not has to do with whether or not the function has roots. Okay? All right. So there's an idea here, which is that each of these algebraic forms, each way of arranging the information, provides us easy to interpret information about how the function behaves, right? And so it's really helpful to be able to change it from one form to the other. And we actually know how to do a lot of the changing already. For instance, if it's in standard form, you already know how to go to general form. You just expand the polynomial. You learned how to do that on the first class, or in the first video. If it's in the factored form, you can bring it to the general form. You just expand. And multiply it all out. And you already know a procedure that goes from the general form to the factored form. We call that, you know, you just find the roots and compare. So the rest of this video is actually all about exploring the different ways to go between these different forms. It turns out that you're already familiar with the procedure that takes us from the general form to the standard form. It's the complete the square. It's slightly modified from the way you've been doing it, but the general procedure is exactly the same. You're just going to have to learn the slight modification to it, but after that, if you can do complete the square to find the roots, you can do complete the square to find the standard form. It's very simple. Then, we're going to talk about how to go between these two. And before I say anything else, or rather before we spend a whole bunch of time talking about how to go from the standard to the factored form, or from the factored form to the standard form, I want you to note something here, which is that even if I didn't teach you how to do these two, you'd still be able to go from the standard form to the factored form. What you'd have to do is start from the standard form, expand it out to the general form, and then find the roots. So you already know how to go between them. If you started with the factored form, you could expand it out and then essentially use the next thing I'm going to teach you to get to the standard form. So the procedures to go between these, you're already familiar with some basic ones, but there are some subtler ones that use some cool arguments that I'd like you to explore, just because they're the types of arguments that you think about when you're thinking mathematically about a system. And so far, Air Popo in the live chat has only said no once. So I guess overall they're happy. Let's talk right now about how to go from the general form to the standard form. It uses a procedure just like completing the square. Okay. So the general form is ax squared plus bx plus c. Remember those, they're capital letter constants, okay? The standard form looks like this. Capital A times x minus h all squared plus k. And I'm going to teach you how to go between them. It looks like the complete the square algorithm. With two slight differences. Here's the slight differences. 1, leave y alone. And 2, the final form of the expression. We're going to take an off-ramp on the complete the square algorithm before we make it all the way to Calgary. We're going to Banff instead of Calgary. Okay? So, without further ado, let's do it for our first example. Here we had it like this: 4x squared plus 4x minus 24. Watch carefully what I do. When you were doing complete the square before, you were trying to find roots of the function. And so it was your polynomial expression on the right-hand side equals 0 on the other side. That's not the starting point of this particular procedure, because what we have isn't an expression where we're trying to find the output, or rather we're trying to essentially there's a y. There's a y here. It's not 0, it's y. Y represents the output of the function. You can't forget that y. It's super important. So we're just going to leave it there. Think of it as a placeholder. So you leave y where it is, and we're just going to do complete the square around it. The next step to completing the square was that we're going to move this term to the other side, remember? So we'll go add 24 to both sides. Okay, you're going to move the constant away. And the next step is, you're going to do that little a b squared b squared thing. So we have to figure out, essentially, what would need to be here for this expression to be a perfect square. Remember? And the procedure was pretty simple. It looked a lot like the perfect square test. You said a squared is equal to that term, and then a is equal to 2, and then b is equal to this term divided by 2 times a. So it's 4 divided by 2 times 2, which is equal to 1. And then b squared is equal, little b squared is equal to 1. And that tells us that this constant here, whatever goes in there, would have to be a 1 for it to make it a perfect square. So I'm going to add 1 to both sides. Plus 1 is equal to 4x squared plus 4x plus 1. And now this expression is a perfect square, which means I can factor it. And you remember how to do that? You just write it as ax plus b all squared. Little a's, little b's. Then you're like, hey, aren't all b's little? And I'm like, well, I went to Japan once and I saw a bee the size of a, like, it was real big. It's like the size of like, it's like the size of like an eraser. You know those like separate white erasers that you can buy in the store? It was like that big. And then I came home from Japan because Japan is terrifying. You write it in its factored form and clean up the right-hand side. So at this point in the game, instead of continuing, when you were doing the complete the square algorithm, you would then take the square root of both sides, etc., etc. This is where we're going to get off the highway. Now I'm going to take this expression and isolate the y variable. So here is our nice friend y. I'm going to bring it out front. I'm going to subtract 25 from both sides. There you go. Although to tell you the truth, that's essentially how we modified it, but we're going to do something slightly different with this. Remember when we factored the perfect square? When I taught you to factor this perfect square and you do this? That's great. I love it. But if you notice something with the form of the standard form, oh, I didn't mean to erase those. The standard form, there's no room in this expression for a coefficient in front of the x. So instead of using this particular form, we're going to rewrite it in an equivalent one that looks like this. A squared times x plus b over a, all squared. This involves essentially exactly the same thing. Watch. We're essentially just kind of filling in the blanks based on the data we already have. But it gives you an expression that looks like this. 2 squared is 4. X plus b over a is 1 over 2 all squared. And so our final form is 4 times x plus 0.5 all squared minus 25, which is what I showed you at the start of the video. Okay? Now it's in its standard form. A x plus k, minus k, I'm sorry, I'll always forget that. Minus k all squared plus h. And so a is equal to 4, capital A. K is equal to minus 0.5, and h is equal to minus 25. I'm just comparing that, that, and that. Keeping note of the sign. The sign's pretty important. So we can glean really useful information out of these three numbers in a very similar way that we glean important information out of the say, the point slope form of the linear. Okay. So, let's try another one. Before I go on, maybe you don't like this. It's understandable if you don't. It's understandable if you want to go back to using ax plus b all squared, because this is much nicer than that. So I'm going to show you a trick. I don't actually use this particular procedure when I do this particular calculation. This isn't the one I use because I'm a pro. I'm going to use a slightly different, slightly modified one that it's a little bit of a shortcut. It's slightly easier. Watch what I do, and then you can try one yourself. Okay. It's exactly the same procedure. Let's start. Y is equal to 3x squared minus 12x plus 16. Start the same way you did before. Move the constant over to the other side of the equation. Y minus 16 is equal to 3x squared minus 12x. Okay. Now, before we do the complete the square thing, I know you want to complete the square. Here's the trick. This is the trick. See this coefficient in front of the x squared? I'm going to divide both sides by that number. This is a hack. Divide both sides by the coefficient of the x squared term. Okay? That gives me y minus 16 over 3 is equal to 3x squared minus 12x. The idea here actually saves us quite a bit of time. That's why we're doing it. So part of saving a lot of time is I'm not going to simplify that at all. I'm going to leave that the way it is for now, because the overall purpose of this is after we finish rewriting the right-hand side, we're going to shift lots of the things on the right over to the left. So I'm going to leave this. I'm not going to simplify it anymore. I just divide by the coefficient there, and you end up with a simplified expression on the right-hand side here. And that's nice. So it's going to be much easier to complete this square, because check it out. A squared is equal to 1. So A is equal to 1. So B is going to minus 4 over 2 times 1. So it's going to be minus 2. So B squared is equal to 4. So I'm going to add 4 to both sides. Y minus 16 over 3 plus 4. Okay. And now I can factor this on the right-hand side. Factoring it's super easy, and I use ax plus b all squared, just like I like doing. A is equal to 1, b is equal to minus 2. Okay. And now I'm going to shift all of these terms over to the right-hand side. It's a little bit tiresome, but it's not that tiresome. Watch. First I get rid of that 4. This 4, I'm going to move it to the right. So subtract 4 from both sides, and you get x minus 2 all squared minus 4. And now this 3, I'm going to multiply both sides by 3. All right, here, hold on. Minus 4 both sides. And now I'm going to multiply both sides by 3. You get y minus 16 is equal to 3 x minus 2 all squared minus 12. And the last step, I'm going to add 16 to both sides. Plus 16, which becomes ta-da! And that's my final answer. So in this one, A is equal to 3. All right, hold on. H is equal to 2, K is equal to 4. Those particular numbers are going to be pretty helpful a little bit later on, so I'm making note of noting them right now. All right, so to review, we're going to try another example, right? But to review, the only difference between what I did in the first time I did it and this time is partway through, before I did complete the square, I divided both sides by the coefficient in front of the x. Doing so simplified this expression dramatically. Made it much easier to find, to complete the square, to find the term to make it a perfect square. It kind of made the stuff on the right-hand side a little bit messier. It made the stuff on the left-hand side a little bit messier, but don't worry about that, because solving for y in this expression is super easy. I just have to like move stuff over one bit at a time. It's like unpacking a moving van. Okay, so let's try another one, huh? Y is equal to minus 2x squared minus 12x minus 13. Oh, gross. Gonna start. Why don't you try it? Pause the video, give it a try. All right, so you're gonna start by moving the 13 over. Plus 13. And now I'm gonna divide both sides by minus 2. So it becomes divided by minus 2. So that's x squared plus minus 12 divided by minus 2x. (6x). And now I do complete the square to this guy. A squared is equal to 1. So b is equal to 6 over 2 times 1, so it's equal to 3. So b squared is equal to 9. So I have to have a 9 on the right-hand side to make that a perfect square. Oh no, I messed up. Let's try this again. Y plus 13 over minus 2 plus 9 is equal to x squared plus 6x plus 9. Okay. And now I can write this as a perfect square. X plus 3 all squared. Now, before I say anything else, you could simplify the expression on the left-hand side, but doing so usually involves mangling fractions, and I don't like adding fractions together. So instead, I'm just going to unpack it one piece at a time. So I'm going to subtract 9 from both sides. Minus 9 from both sides. And then I'm going to multiply by minus 2. Minus 2 times x plus 3 all squared plus 18. So times minus 2. And then, so what doing the trick I just showed you does in terms of the operation of the thing, minus 13. Wait, hold on. What it does. I'm getting ahead of myself. Subtract 13 from both sides. What dividing everything by the coefficient in front of the x squared does at the start is it kind of does a runaround. Sometimes you've seen it before. Sometimes you have expressions when you're, say, using the complete the square algorithm. Sometimes you get expressions that have lots of like weird square roots and stuff in them. This avoids all that mess. So it's great. Sometimes you can't get away from having square roots, but sometimes, like in some of the worksheets, those square roots in the end answer will all go away. And if you divide by the coefficient of the x squared right at the start, you get rid of that ambiguity, and it just makes life easier. So a is equal to minus 2, and k, h is equal to minus 3, and k is equal to 5. Where did this come from? I'm comparing this to a x minus h all squared plus k. All right, so in the worksheet, you're going to get lots of practice doing this because it's super useful. And, may I add, you've just learned how to go from the general form to the standard form. Hooray! So at this point in time, if you want to stop watching the video, you can. You'll miss out on some pretty useful things, frankly. But one question you might want to know is, how do you go between the standard form and the factored form? Because there's a way to do each of these. And there are some actually pretty useful lessons about how to interpret polynomial and function behavior that can come out of learning how to go between these. So even though you don't really need to learn how to do them, it's still fun and it's still worth it. So let's talk about how to go from the standard form, which is y is equal to a x minus h all squared plus k, to the general form, to the factored form, which is y is equal to a x minus x0 times x minus x1. Okay, so how did we do this before? This is something you already learned how to do in a previous video. Key to the method that you used to figure out what the factored form in the prior lesson was, you had to complete the square to figure out what the roots were, right? Because if you know what the roots are, I guess that's one. If you know what the roots are, you can just fill in the blanks on this particular calculation. So, hey man, that's pretty cool. If you know what the roots are, you're home free on figuring out what the factored form is. And I have good news for you. All that work we did getting into the standard form, where we pretty much completed the square, we can just finish the job to figure out what the solution to the standard form was. So, in other words, all we have to do is figure out the roots. Find roots. That's mission 1. How do we do it? Set y to equal 0. If you set y to equal 0 in this equation, you're saying, I want the output to be 0. The values of x that make the output of the function 0 are called the roots, and we can find them, essentially using the same thing. So let's try for our first example that we worked with at the start of the video. That polynomial looked like that. Hey, it's a nice quadratic, okay, in standard form. The trick to this is I'm going to set y to equal 0. I want the output to be 0, and I want to figure out what input corresponds to that output. Now what? Solving this equation is actually pretty easy. Do not expand it. If you expand it, you're turning it into the general form. It's actually really easy to find the answer when it's in standard form. All we do is we try to isolate x. So first off, you're going to move this thing to the other side, 25. Okay. And now you're going to divide it by 4. All right, here, I'll just set y to equal 0 in the first step. Second step, I added 25 to both sides. I'm moving that constant over to the left-hand side. I'm moving k over to the left-hand side. The next step, I'm going to divide both sides by a, that expression. Okay, so it's 25 over 4 is equal to x plus 0.5 all squared. And if you want to write that out as a decimal, you can. The next step here is I'm going to take the square root of both sides. Because this is essentially how completing the square, This is, okay, so you know how I was like, this expression is me completing the square and then getting off the highway on a particular off-ramp before we get there. From here on, I'm getting back on the highway. How did I finish completing the square to find the roots? You took the square root of both sides, right? So square root of 25 over 4 is some number. Don't forget the plus or minus in front of it, and the left-hand side is. So you get out your calculator and you calculate it. It's 5 over 2, so it's plus or minus 2.5. And then you isolate x. And this comes out to two answers. There's minus 0.5 plus 2.5, which is equal to 2, and minus 0.5 minus 2.5, which is equal to minus 3. And so the factored form of this is going to be x minus 2, x minus 3. Or alternatively put, x minus 2, x plus 3. But wait, I thought there was a coefficient here. There is. Don't forget that coefficient. Guess what, guys? It's whatever number's out front here. It's that number, 4. That's the coefficient. Just write that number in front of it, 4. There. Now it's in its factored form. Okay. Let's try another example. Maybe you can try it. I'll write it out, you give it a go, maybe pause the video, and then I'll walk you through it. Y is equal to 4, x minus 2 all squared minus 16. So I'm going to set. All right, pause it. All right, welcome back. 0 is equal to 4, x minus 2 all squared minus 16. So you set y to equal 0 because you're looking for the roots. Add 16 to both sides. Divide both sides by 4. Take the square root of both sides. So it's 2 is equal to x minus 2 plus or minus. And then isolate x. So I'm going to add 2 to both sides. 2 plus or minus 2 is equal to x. So x can be 2 plus 2, or it can be 2 minus 2. So it can be 4, or it can be 0. And so the factored form is going to be x minus 4 times x minus 0, and then the coefficient out front is going to be that number there. So if you want, you can rewrite this as 4, x minus 4 times x. Okay, so we said before that not all quadratics can be factored, and that's definitely true. So not all quadratics have a factored form, and you know that from the previous video. But can you see that that's true in this case? Sure. So for example, this one. Let's try finding its factored form. Oh, I should be trying to write nicer here. Minus 4 is equal to x minus 2 all squared. When I take the square root of both sides, you plug that into the calculator and it says doesn't exist. And it doesn't exist because there's no factored form. So if you try to take the square root of there, you're done for. That's it. Doesn't exist. There's another case here where the factored form, how about this one? Let's change this one to the factored form. All right, so there's no constant to add, so it's divide both sides by 4, I guess. And I take the square root of both sides, so it's 0 is equal to x, or plus or minus 0 is equal to x minus 2. So x is equal to 2. So y is equal to 4 times, 4 is this coefficient, times x minus 2 times x minus 2. Oh, hey, cool. Check it out. It's already in its factored form, right? Yeah. Because this expression just means that this is the function, x times x minus 2, x minus 2. So if there's only one root, the general form and the factored form are the same. So this is no root. What happens if there's no root? And this is what happens if there's one root. If there's one root, you're already there. If there's no roots, well, you'll find out soon enough. Okay? It should be very similar to completing the square. Okay. Now, at the start of this, I mentioned that each of the different forms... Well, hold on. Let's take stock. What do you know how to do now? You know how to go from the general to the factored form. That was in the first lessons. You know how to go from the factored form to the general form. That's expanding. You know how to go from the standard form to the general form. That's also expanding. First part of the video was all about going from the general form to the standard form. That was a modification of the complete the square procedure. Okay. Now you know how to go from the standard form to the factored form. Essentially find roots by setting y to equal 0. What we crave next is going from the factored form to the standard form. Okay? But being able to explain how that works and why it works the way it does, we need more insight. We need the ability to look at and interpret these functions. So we're going to take a little side tour and talk about what each of these expressions for the functions is telling us. What the general form tells us, what the factored form tells us, and what the standard form tells us. Okay? Once we've cracked that, going from the factored form to the standard form is actually quite easy. Man, there's a lot in this video, isn't there? There's an old story that everybody talks about in India where they say 3 wise men in India are blind and they're taken to see an elephant. And they're blind and they've never seen an elephant before. And so they go up and they touch the elephant. And each blind person touches a different part of the elephant. So one of them goes up and touches the ear of the elephant and says, oh, an elephant is like a palm tree. It's got these great big leafy parts. And then another one goes over and touches the trunk and he says, oh, the elephant is like a snake. And the third person goes over and touches the tail and says, oh no, it's like a rope, right? The moral of the story is you can have the same thing, the same function, and all these different forms that we're talking about are us talking about different specific parts of the elephant. It's the same elephant, we're just approaching it from different directions. And depending on the direction you look at it, depending on the way we've algebraically arranged it, different information is easily apparent that it might not be from a different direction. So let's talk about those. The general form looks like this. Okay. That is the Y-intercept. That number. So if somebody goes, y is equal to 3x squared plus 4x minus 7, you know that the Y-intercept, if you were to graph it, the Y-intercept would be minus 7. Why? Why is that the case? It's the case because all the other terms in this expression have an x in them. So when x is equal to 0, each of these highlighted terms is 0, and y must equal the last term. Okay? So it's the only term that doesn't depend on x, so it's the only term left when x is equal to 0, which is essentially where the y-axis is. This is actually going to be a pretty useful thing to know when we graph it. But there's another aspect to this that we mentioned at the very start, which was this coefficient a. That coefficient is super important to the behavior. What do I mean by that? Well, the output depends on the input, okay? The input determines what the output is, okay? But you can guess what kind of number you're going to get for really big values of x. Really big positive or negative number that coefficient is going to determine if y is a really big positive number or a really big negative number. Let me elaborate on that. In other words, all of these polynomials are going to behave in a similar way. It's always going to be only positive or only negative. It's only going to give you a really big positive out or a really big negative out, depending on what the value of a is. So in terms of what the function does when the input is really, really big, a is the most important term. Let me elaborate with two examples here. Okay, so in both these cases, let's look at what happens when x is equal to a really, really big number, 1,000. Is y going to be a positive number or a negative number when x gets really, really big? That's the question we're going to ask. Well, if you think about it, when x is a really big number, you can think about this expression in terms of individual parts and how the individual parts contribute. So the first term is 3 times 1,000 times 1,000. And the second term is 4 times 1,000 by itself. And the third term is 2. So the first term is going to be 3 million. And the second term is going to be 4,000. And the third term is going to be 2. So you see, when x is a really, really big number, you're going to get a number 3 million. 3 million is way bigger than 4,000, right? Like, it's so much bigger that the answer is approximately 3 million. When x gets really, really big, the size of the first term overshadows the size of the second and third term. And so, the value of y is going to depend most on what the first term is doing than what the second or third term is doing. Allow me to say this in a different way. The actual output here is 29959. Wait, hold on. Nope. 6002. Okay. If I compare this value to just this value on its own, $299,600,002 divided by 3 million. This value, this accurate value, is the difference between this and our approximate 3 million number is only 3998 divided by 3 million. The difference between our approximate number and our accurate number is only 0.1% of the number. Okay? So when x becomes really, really big positive or a really, really big negative number, the output y mostly depends on what that first term is, and very little depends on these other terms. These coefficients would have to be really, really big for it to matter at all. And the bigger and bigger the number is, the more the first term dominates what the actual output of y is. Okay? That's the lesson. So how do we determine what kind of number is going to come out? Well, if you think about this in terms of two parts, x squared is always a positive number. It's positive whether x is a positive number, x squared is positive whether or not x is a negative number. And so the value of y depends a lot. The sign of the value of y depends entirely on what the coefficient is here. If a is positive, then for big x bigger than 0 and x less than 0. So when x is a huge input, negative or positive, y will be positive. This is what we mean when we're talking about the behavior of the function. How does it behave for really, really big values of x? Is it a big negative number or is it a small negative number? Let me repeat the argument for this case. When x is equal to, let's go 10,000. The first term is going to be minus 8 times 10,000 times 10,000 plus 80 times 10,000 plus 2. The first term is minus 800 million. The second term is 800,000, sorry, which is a big number, but way smaller than 80 million. And that 2 doesn't even make a ding, right? And so for large x, the value of y is going to be a large negative number because of that coefficient there. Okay? So what we're doing is we're saying, hey, if we look at the coefficient of the first term, in the general form, ax squared plus bx plus c, when x is a really large number, positive or negative number, then it will be approximately equal to ax squared, because the bx and the cx are tiny numbers compared to what this number is going to be. And thus, y will be positive, a big positive number if a is positive, and y will be a big negative number if a is negative. And so we can determine information on the behavior of what this polynomial is doing based on these arguments about the leading term, we call it. Okay? We can make a similar argument with the factored form. Let me write out the factored form, and I'll walk you through that argument. A x minus x0 and x minus x1, where there are roots at x is equal to x0 and x is equal to x1, right? So for instance, y is equal to 6 times x minus 3, x plus 5. You know the roots are 3 and minus 5. We mentioned before that the power of the factored form is that you can tell what the roots are. That said, you can still talk about what the value, how the function behaves. How function behaves at large x, both x positive and x negative, based on that coefficient a. How does that work? Let's think about it like this. Okay? If x is equal to, I don't know, 1,000, is this term going to be positive or negative? It's going to be positive, because 1,000's really big, bigger than the root. What about this term, positive or negative? It's going to be positive, because that is way bigger than the root. So both of these terms, when x is a really big number, will be positive, and the value of y will depend entirely on whether that term is positive or negative. And that shouldn't be surprising to you. But here's an alternative way of thinking of it. What if x is a really big negative number? Negative 1,000,000. Okay? Is this term going to be positive or negative? It's going to be negative. Because regardless of that minus 3, that minus 1,000,000 is going to be bigger. Is this going to be positive or negative? You guaranteed when x is a really big negative number, they're both going to be negative. A negative number times a negative number is a positive number. And so the behavior of y, whether y is positive or negative, depends entirely on what this coefficient is. If the coefficient is positive, then y for big values of x is going to be positive. If the coefficient is negative, then y is going to be negative. Because in both cases, sorry, for really big inputs, once you're really far away from the roots, you can say, okay, if I'm really far away, both of these are going to have the same sign, and then the overall sign is going to be determined by that term out front. Okay? So let's talk about interpreting in exactly the same way, but in standard form, because that's the real trick. What does standard form tell us? All right, I'm going to write out two standard form expressions so we can use these to argue. (200) and y is equal to plus 6, x plus 5 all squared minus 200. There we go. Both of these are in standard form. Now, when x is really big, is that term going to be positive or negative? Well, that term's an expression all squared. So when x is really, really, really big, it's going to be a really big number all squared. Similarly here, really big number all squared. You'll note that the way the standard form is written, the thing afterwards doesn't depend on x at all. So if x is a huge number, guaranteed the first term is going to dominate over the second term. Guaranteed when x is huge, this term is going to be way bigger than this term. It might be positive, it might be negative. What determines if the first term is positive or negative? What determines if this is positive or negative? This coefficient. If it's minus 3, when x is a really big number, this is going to be a huge negative number. That's 6. So when x is a really, really big number, and this is a huge value, this term's going to be a positive number. And so in a similar vein of arguing, when x is going to be really big or really small, the term a determines how y behaves. Okay? But the standard form gives us an additional piece of information, a lovely, lovely piece of information. We can still think about these things as two different parts. That part and that part. This part depends on x, and this part doesn't. This part depends on x, and this part doesn't, right? But there's more to it than that. In this expression, that term there can only be positive. This term here can only be positive. Can only be positive. What's the smallest value it can be? Smallest value is 0. It's always a positive number, so the smallest it can be is 0, and it's 0 when x is equal to whatever that value h is. So in this case, the smallest this expression can be is 0 when x is equal to minus 4. This expression here, the smallest it can be is 0, and it's 0 when x is equal to minus 5. Does that make sense? Okay. Now, here's the fun part. When the part that depends on x is its smallest, all that's left behind is this number back here. When the part that depends on x is smallest, that constant at the end is going to be either the maximum or the minimum of the function's outputs. It's the smallest it can be or the biggest it can be. Let me elaborate on that a little bit more. We'll do some specific examples. Y is equal to minus 3 times x plus 4 all squared plus 200. Okay, let's walk through it. The smallest this can be and it's 0 when x is equal to minus 4, right? But this whole thing is going to always be negative. For any value of x. Like I said, this part of it is always going to be positive. So a positive number times a negative number is a negative number. So this first term in our expression is always a negative term. And that means that the function is going to get more and more negative depending on x. The farther from x is equal to minus 4 our input gets. Right? And so the overall value is going to get smaller and more and more and more negative, and thus y is equal to 200, which is the output when the first term is at its smallest, is the maximum value. This is lovely because when it's in its standard form, we can interpret what the maximum value of the function is going to be. Let's try another one. So, this term here is always positive. The smallest it can get is 0 when x is equal to plus 5. Okay? Now, this whole first term is always a positive number. And so y is more and more positive the farther our input gets from x is equal to 5. So the farther away our input is from that number, the bigger the output is going to be. And so that value, minus 200, is the minimum output of the function. Do you see how this argument works? I hope so. It's really helpful to be able to think through things yourselves. Sometimes you can't remember each and every aspect of a rule, and so it's helpful to see these things yourself. Let me write it out in standard form. Y is equal to a times x minus h all squared plus k. Like I said, the a, the h, and the k all dictate what the function is going to be doing. All right, hold on. If a is negative, then it means the function gets more and more negative as x gets big. And so the function is going to have a maximum, a number it's getting farther and farther away from. If a is negative, y has a maximum. If a is positive, y has a minimum. And the maximum output is going to be k, and it happens at x is equal to h. Similarly, the minimum output is going to be k, and it happens at x is equal to h. And so what we can do is we can just look at a function in standard form, and you can tell whether it has a maximum or minimum and what value it's going to happen at. So for example, y is equal to minus 3, x plus 5 squared minus 3. So a is equal to minus 3, h is equal to minus 5, k is equal to minus 3. So from these pieces of information, from the first one, you can tell it's going to have a maximum. The value of that maximum is going to be this number, and it's going to happen at x is equal to minus 5. Okay, so at this point in the game, you're like, oh, I thought you told me that I thought we were building up to talking about going from the standard form to from the factored form to the standard form. What does this have to do with the thing? It has everything to do with the thing. We're going to get to graphing this in a second. But if you haven't noticed, there's a relationship between the properties of the graph and the properties of the function. Okay? So, the max or min value is the vertex. That's an important clue. Before I go on, I want to emphasize something here with all three different forms of the function. In all three forms of the function, you define the parabola. You define the quadratic function in terms of knowing three numbers. These three numbers are going to be different. Even if it's the same function, the three values are going to be different in each of these cases. A is going to be the same. But h and k in this one are going to be two different numbers than x0 and x1 in this one, and are generally going to be two different numbers than b and c in this one. Okay? But you only need three numbers. And so the idea here is, if I can figure out what those three numbers are, I'm golden for switching between them. Sometimes it's an easy thing. All I have to do is expand. But when I was moving from the standard form, from this form, to the factored form, essentially all I needed to do was figure out what this number and that number were, right? A is the same, so I just had to figure out what the roots were, figure out what the two numbers are. In this case, when I'm doing it in the opposite direction, when I'm going from the factored form to the standard form, I need to figure out what these two numbers are. And it's not all that tricky, because these two numbers are where the function is the minimum and what the minimum value of the function are. And those aren't hard to find. Those are super not hard to find, because we know that these correspond to a parabola, and that parabolas have that line of symmetry going down the middle. Why? The vertex where on the x-axis the vertex is halfway between the roots, if they exist. Okay? So watch. Y is equal to 3 x minus 2 times x plus 6. All I have to figure out is where is halfway between the roots. If you want to draw a picture, that's fine. Minus 2, 6. You just need to figure out where halfway is between those. So this overall distance here is 8. So halfway the length of 8 is 4. So this distance here is 4. And so this location must be x is equal to minus 2 plus 4 is equal to 2. The maximum point must be at x equal 2. And then so that must be your value of h. How do you figure out the value of k? Wait, what'd I do? Oh my gosh. Forgive me. Oh, I messed up. Start again. All right. The roots here are at -2 and +6. I had to change the equation so the roots were there. I'm sorry. It's been a long video. So the distance between them is 8. Half of 8 is 4. So the x-coordinate of that location is x is equal to -2 plus 4. It's at +2. And so h must equal +2 for this specific polynomial, maybe not the last one I wrote out. How do we figure out what the value of k, though, is? K is the maximum or minimum value of this function. So all I have to do is plug this number into this function. 3 times 2 plus 2 times 2 minus 6. 3 times 4 times -4. So that's 3 times -16. So that's -48. So you plug in the value. First you figure out the point halfway between the two roots. That tells you that number. And then you figure out the y value corresponding to that. And so that tells you that your standard form is going to be x minus 2 plus -48. What goes out front? 3. Ta-da! I'm not sure how often I'm going to ask you to do that. It's pretty fun, but we're getting pretty deep in the weeds on what polynomials are doing. So let's just review and then finish up our thing. Here's the medicine wheel for our particular topic. Oh, geez. We had 3 different ways to write the same polynomial. There's the general form. Y is equal to ax squared plus bx plus c. There's the factored form. Y is equal to a times x minus x naught plus x minus x1. You know how to go from here. Ooh, how about a smaller pen? Let's go there. You know how to do that one already. You knew since several videos ago. That said, we can also put it in something called the standard form. Y is equal to a x minus h all squared plus k. And the idea is, if it's in the factored form, it's easy to put it in the general form by expanding. If it's in the standard form, it's easy to put in the general form by expanding. And then we started going, okay, we can use the general form. Completing the square gives us the standard form. Factoring it gives the factored form. We can then use finishing completing the square to go from the standard form to the factored form and go back and forth. But the overall idea is, the point to all 3 of these different ways of writing it was that all of them told us something different about the function's behavior. The value of a tells us if it's an increasing function or a decreasing function, whether the function is a big negative number or a big positive number for a big value of x. In this general form, that constant told us the y-intercept, which is actually a kind of a handy thing to know. In the standard form, these 2 numbers told us the maximum or minimum of the output of the function. And in the factored form, this tells us what the roots of the function are. And so in each of these different forms, they tell you a different aspect of the behavior of the function, And knowing that information allows us to go from the factored form back to the standard form. Okay? Well, that's it for now. We'll do some graphing next episode. Thank you. Hey everybody. Oh wait, hold on. I gotta change the thingy here. If I see graphing parabolas. Okay. So here we are trying to graph parabolas. Graph quadratics. The objectives on this is, given the standard form, you can sketch the graph. Given the factor form, you can sketch the graph. Yeah, it's not tricky. We'll show you. So let's start. Hold on. Okay. Here's my x. Here's my y-axis, and y is equal to x minus 2 all squared minus 3. Let's plug some numbers into this and see where we get. So when x is equal to minus 2, this is equal to minus 2 times minus 2 is 4. 4 squared is 16. Minus 3 is... okay, how about a different one? How about x is equal to... Actually, you know what? I'm going to go... I can use a truncated x. No, I can't. How about x is equal to 0? Cool. 1, 2, 3, 4, 5, 6. Okay, when x is equal to 0... it's minus 2 all squared is 4, minus 3 is 1. When x is equal to minus 1, it's minus 3 all squared is 9, minus 3 is 6. 1, 2, 3, 4, 5, 6. There. Okay, so when x is equal to plus 1, 1 minus 2 all squared is 1, minus 3 is minus 2. Minus 2 is there. When x is equal to plus 2, that's 0 squared minus 3. There. And when x is equal to plus 3, that's 3 minus 2 is 1. 1 all squared is 1, minus 3 is minus 2. When x is equal to 4, it's 4 minus 2 is 2, all squared is 4, minus 3 is 1. When x is equal to 5, 5 minus 2 is 3, 3 all squared is 9, 9 minus 3 is 6. 1, 2, 3, 4, 5, 6. Oh, really? 1, 2, 3, 4, 5, 6, 6. I think this point should be moved down 1. 6. Okay. So, if I wanted to plot this function, and you can plot functions, remember, we've talked a lot about plotting functions. It's just another way of displaying what the function is. Essentially, you get a line that looks like this. Which is a parabola. Hooray! It has a vertex. It has an axis of symmetry. See, look. Burp, burp, beep. Draw a horizontal line. any point. The distance between the two points is the same. How about if I choose a different horizontal line? These two are mirror image points. This one is 4 away. This one's 4 away. These two are mirror image points. This one's 2 away. That one's 2 away. These two are mirror image points. This one is 1, 2, 3, 4, 5, 6 away. And this one is 1, 2, 3, 4, 5, 6 away. Yeah? It's got an axis of symmetry. It's a parabola. Guess what? All quadratics, graphs of quadratic functions are parabolas. And if you didn't notice from the last video, we can use that information to actually save us a bunch of work. Like I said before, we can use, say, knowledge about where the roots are to figure out where the vertex is. Oh, by the way, what about all that stuff we said? Well, for one thing, roots. Roots, on the one hand, roots are places where y is equal to 0, and you find the values of x where y is equal to 0. Like we said in our graphing one, roots are where the line intersects the x-axis. Okay? And so this counts as a horizontal line. These are mirror points, and so we can use them to find the axis of symmetry and thus the vertex. I'm getting ahead of myself. How does the vertex fit in with all this? Because it's a parabola, it's going to have a maximum or a minimum point, right? It's going to have a bottom to the U-shape or a top to the upside-down U-shape. And that point corresponds to the maximum or the minimum output. So the vertex is okay, so the coordinates of the vertex, x vert, y vert, is the max min output of the function. Which makes sense. If you think about this as a function and you're like, oh, for this value of x, this is the value, this is the output. Oh, geez. Holy crow. This grass is too messy. Oh, geez. Let me remake that point just a second ago. Okay. We can think of this line as a function and use it to say, okay, when x is equal to 2, when that's the input, this is the output. Y is equal to, I don't know, what is that, 6? 1, 2, 3, 4, 5, 6. Right? And so as we change the input of x, you get different values of y. Change the input of x, get this value of y. If you think about it, in terms of plotting what the y values are, as I move away from the vertex, in this case, I'm getting bigger and bigger values of y, right? And at the vertex, that's the input corresponding to the minimum output in this case. Okay? So those geometric features and the algebraic features are reflected in each other. Knowing about the algebraic features tells you what the geometric features are, and knowing what the geometric features are tells you about the algebraic features. It's pretty lovely. Okay? Okay. So, let's do a quick thing about sketching graphs. There's a difference versus sketching and plotting a graph. If I plot a graph, I want to be able to use it to find the output for any input I give it. So you want it to be super, super, super accurate. Okay? If you're sketching a graph, it means you just kind of want you don't want a vague sense. You want to see the basic features. Is it an increasing function or a decreasing function? Are the lines of it going up or down? Where around is its maximum? Where's its minimum? That kind of thing. So, it's not too tricky. The deal here is, in essence, when I talk about sketching, I don't want each and every point to be super accurate. You want to save time, but you also want to give an illustration that has the basic properties of that function on it. So we're going to teach you some sketching. Now, for linear equations, definitely sketching is the same thing as plotting, because I mean you can make a ruler and then you're good. But for these curved lines, all I need is a sketch. Okay. So here's how a sucker sketches this graph. They just choose a whole bunch of inputs, x equal 1, x equal 2, x equal 3, and they find the output for each of these, blah, 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 and then they plot them all on the graph and they draw a line through it. That's the worst way to live your life. Takes forever, looks terrible. So instead, what we're going to do is we're just going to glean the basic pieces of information on this and use it to sketch. Okay? Oh, geez, that's the worst axis I've ever seen. All right, so you draw your x and y axis, x, y. And we're going to read the information off of this graph. It's going to tell us information that we can use to sketch it. Okay? So for instance, you can say, okay, h is equal to -1 or +1, and k is equal to +3. We know that this is the max, this is the input that makes this function the output. It's going to be the maximum or minimum, right? That's the purpose of those particular numbers. That's how we interpret them. And what it means is that when x is equal to y, 1, 2, 3, 4. 1, 2, 3. Is it means that the vertex of the function is going to be at that point. So you put it there. Okay? And then you know that because this here is a negative number, because a is a negative number, it's going to be decreasing. It's going to get more and more negative as time goes on. The graph's going to be pointed down like that, and so the graph's going to look like that. How do I make this better? Well, the deal is that this is an okay graph. It has some basic information on it, and we like that. But we could figure out more information to put on it. Okay. Let's start there, though. I'll give you another one to try yourself. Okay. So how about this one? Y is equal to 4 x minus 2 squared plus about minus 3. Let's start by sketching what this graph looks like. Where is its vertex? 1, 2, 3, 4, 5. It's the x-axis. Here's the y-axis. What we're going to do is we're going to interpret from this, so h is equal to 2 and k is equal to -3. That means that the vertex is going to be at 2 minus 3. Okay? So 2 minus 3 is right here. That's where the vertex is. And then the value there, 4, tells you that the function is going to be increasing. When x gets really big, it's going to be a big positive number. So it's going to look like that. So if you want to, you can sketch the graph and say, oh, it looks like that. Now, that's not a very good graph. I mean, it's okay, but it's not super great. Okay? It'll do for now. We'll revise it in a little bit. Here's a function in its factored form. What can this tell us? 1, 2, 3, 4. 1, 2, 3, 4. All right. -1, -2, -3, -4. All right. In this one, we don't know what the vertex is, right? You don't know where the vertex is. Instead, this is the factored form, so you know what the roots are. So one of the roots is going to be at x is equal to +2. So you know that the function crosses the line here. And the other root is at x equals -3. So the function crosses the line here. Do you know if the function's going that way or that way? Well, the coefficient here, a, is equal to 4. That's a positive number, so you know that the line's going to get bigger over here. So the graph of the function that looks like that. That's not a bad graph. The previous two aren't bad graphs. They're mediocre graphs, but they're not bad. They'll do the job. They tell you some super information, like the vertex is around here. That's a happy, important thing to know. Similarly before, this graphs tell you, well, the root is somewhere around here. The roots are somewhere around here. Those are super helpful things to know. Sometimes you don't even know where to start looking for roots, or whether the roots even exist. Drawing a graph like this tells you if the roots exist. Fantastic. Okay. Let's try one more. And then we'll go back and we'll make each of these graphs better. How about this one? Y is equal to 2x plus 2 all squared plus 1. This is in standard form. You know what? I'm going to move this axis down here, because I know something that you don't. Boop, boop. That one. That one. All right. So -1, -2, -3. It's in standard form, so that means it tells us about its vertex. What are the coordinates of its vertex? Man, after you've spent so much time in the mind trying to figure out what the vertex is, it's pretty sweet. Okay, so h is equal to -2, k is equal to 1. That's where the vertex is. 2, 1, here. Okay, so which way is it going? Is it going like that, or is it going like that? Well, a, the coefficient here is equal to 2. That's a positive number, so it's shaped like that. So you know that the function is going like that. Whoa, don't go away. Right? So here's a sketch. Like I said, it's not a bad sketch. It's a kind of a crummy sketch, but it's not too bad. It tells us useful information, right? Like, for instance, does this have a root? Will this expression have a root? No, it doesn't cross the x-axis anywhere, so you know that it doesn't have a root. So maybe you don't want to waste any time trying to find that root. Pretty cool. Okay, so now let's talk about how to make these graphs better. I guess we can start up here with this one. How do you improve? Well, the idea here is that if you write the graph in a different form, you can get more information. What other forms do we know how to write it in? Well, we can write it in its factored form, or we can write it in its expanded form. Often expanding it's the easiest thing. So let's expand this. 4x minus 4x plus 4 minus 3, y is equal to 4x squared minus 16x plus 16 minus 3. So y is equal to 4x squared minus 16x plus 13. Well, already we've improved our graph. We know that the graph's shaped kind of like U, an upward pointing U, but we don't know anything else. Now, you can see it's Y-intercept, so it crosses the intersection way up here. I'm just going to draw it up there. I'm going to call that x equal to 13, y is equal to 13 for now. Okay, so you know it crosses the axis way up there. Why is that helpful? Is that very helpful? The answer is that's more helpful than you'd think, because we know where the axis of symmetry is, right? And so this point here is at 1, 2, 3, 4. Oh wait, I guess 2. So 1, 2, 3, 4. You know that its mirror image is going to be over here. And now I've got 2 points that I can draw this line through. And this gives you a much better sense of where the roots might be. Yeah? So it's already more useful. Let's continue our journey on over here. How about this one? This too can be improved, knowing where the y-intercept is. Let's expand this. So it's x squared minus 2x plus 3x minus 6. So it's whoa! I made some pretty bonkers thingies here. So y is equal to 4x squared plus 4x minus 30. No, not 32, 24. Okay. Well, already we have these 2 points, and now we have a third point here. Way down here at, I guess, minus 24. And so knowing that third point is going to help us shape the graph, right? Cool. What about this crummy one? Already, you know where this 1 point is. Let's expand this out. To x squared plus 4x plus 4 plus 1. 2x squared plus 8x plus 8 plus 1. Oh, gross. I haven't made a single polynomial here that I can graph in a single one. I'll give you one to graph properly in a second. So the idea, so gross. The idea here is that way up here at y is equal to 9, that's where it goes through the x-axis, so the y-axis. And then, because you know where the axis of symmetry is, you know that it has a mirror point over here, and you can use these to help you draw your parabola. Okay? And this continues to be actually fairly interesting, because for this one, you know that there's no third form for the graph. But for these other two, you know that there are third forms of writing the graph that you can use. Aw. This poor guy didn't even get a chance. All right, let's find its y-intercept. Minus 2x squared minus 2x plus 1 plus 3. Y is equal to minus 2x squared plus 4x minus 2 plus 3. Y is equal to minus 2x squared plus 4x plus 1. So the y-intercept is at plus 1. And hey, you know that it goes through that mirror point as well. Yeah, so you know it shapes something like that. You can add to this a notion of where the roots are, if it exists, because the roots are if you find the roots, that's going to give these 2 more points and add to the impressive shape. So the long and the short of it is, Each different form of your equation is going to tell you something super helpful about what the graph looks like. And so we already know how to change forms. We can change it to its different form and use each different form to give you a different piece of information. And the total is, usually you can find 5 different points that you could use to draw the line through without much work. It's just a little bit of algebra. So, let's try our own here. Y is equal to x minus 1 all squared plus 5. No, minus 5. Okay. I want you to try graphing this. We'll write it out all 3 different ways, and then we'll try graphing it, okay? I think this one works. No, it won't. Hold on. Not 5. I want it to be 4. Yeah, that'll work. All right. Okay, so we're going to graph this, and the graph is going to be really good. I mean, part of the reason it didn't work before is that most of the graphs I was drawing were based on interpreting the equations, figuring out the one useful information from it. But 1, 1, 1. Okay. 1, 2, 3, 4, 5, and then squat that axis down. 1, 2, 3, 4, 5, 6, and this will be minus 2, minus 4, minus 6, minus 8. All right, let's get to plotting. So it's in standard form. So let's figure out where the vertex is. The vertex is at h is equal to 1, k is equal to minus 4. So it's going to be right there. That's the vertex. Okay. Is it going up or down? Well, the value of a is equal to 1, which is positive, so you know that it's going up like that. So it will have roots. Let's figure out where the y-intercept is by expanding it. X squared minus 2x minus 1 minus 4 plus 1. Y is equal to x squared minus 2x minus 3. So the y-intercept is going to be at minus 3, and because we have our axis of our symmetry, you know that there's going to be another point over here. All right, next one. Let's try to factor it. So this becomes 4 is equal to x minus 1 all squared, so it becomes plus or minus 2 is equal to x minus 1. So it's x is equal to 1 plus or minus 2. So it's at 1 minus 2 and 1 plus 2. So that's a minus 1, and that's 3. So 3 is over here, and minus 1 is over here. There we go. 5 points. And then you can draw your parabola going through all 5 points, and you can say, ah, look at that bonny graph I just sketched. Okay? Great. Any questions? Do you want to try one yourself? How about trying this one? Minus x plus 2 all squared plus 1. 2, 3, 4, 5. Minus 1, minus 2, minus 3. That's a 2, 4. I'll count up by 6. And then minus 2, minus 4, minus 6. All right, let's see what this tells us. H is equal to minus 2. K is equal to plus 1. So the vertex is at here. And so that's where the axis of symmetry is. Is it A is equal to minus 1, so it's going down like that. So there will be roots. Cool. If there are no roots, you can still have the 3 points by using the vertex and then the Y-intercept. So let's find the Y-intercept right now. Minus x squared plus 4x plus 4. So y is equal to minus x squared minus 4x minus 4 plus 1. So the y-intercept is going to be at minus 3, and then you get a second point for free because you go 1, 2, 3, 4. There. Mirror image. And now let's find the roots, because why not? So, oh wait, okay. Minus 1 is equal to minus x plus 2 all squared, divided both sides by minus 1. Take the square root of both sides. So x is equal to minus 2 plus or minus 1. So x minus is minus 2 minus 1. X plus is minus 2 plus 1. So that's minus 3 minus 1. So you go to see that point and that point. And then you can draw your parabola. Oh. All right? Any questions? All right. Well, that's it. The deal here is that behavior. You spent so much time learning to go from the general form to the standard form to the factored form. But all of that work we put in was really useful because the behavior of our function reflects in its shape. And so the standard form tells you about information about the shape, and the factored form tells you information about the shape, and the general form tells you information about the shape. Which means that using simple algebra, we can either find 3 or even 5 points that you can use to sketch your parabola. Okay, that's it for this episode. See you.